hypothesis testing, and confidence intervals for slope. We're going to start with this example, and the first 2 pages I will show you the computer printout and an idea of a confidence interval, and then the second 2 pages I'll actually do a 5-step hypothesis test and a 4-step confidence interval. So our first example is right here, and it says good runners take more steps per second as they speed up. Here are the average number of steps per second for a group of top female runners at different speeds. And this chart got a little messed up. So 15.86, a runner with an average speed of 15.86 feet per second takes about 3.05 steps per second. And they should line up like this. Okay. If we want to look at how many runners there were, 1, 2, 3, 4, 5, 6, 7. So N equals 7. Now, on the AP exam, one could be faced with a computer printout relating to this data. And it might look something like this. We've seen this before, where it gives you what R squared is, otherwise known as the coefficient of determination. And that tells you that 99.8% of the change in Y, or the steps per second, can be explained by the change in X, or the speed that the runner is going. If we were to square root that, we'd get the R, and this R would be positive because it looks like they do more steps per faster speed. This S is our standard error for the line of regression. We talked about that with Barbie Bungee. And then our degrees of freedom comes from the formula of n minus 2. So in this case, 5. Now going back and down to here, okay, constant, well that is going to be the y-intercept, and based off of our calculator we actually call this, if we do linear regression, the number 8, whereas a plus bx, okay, in our calculator this would be our a, or our y-intercept, and this would be our b, in other words our slope. Okay, so y-int and slope. This is the standard error of the y-intercept, and this, and I'm going to highlight it because we're going to use it later, is the standard error of the slope. All right, so from this we should be able to glean that this is the y-hat equation, or the prediction equation. The predicted number of steps, it's the y-intercept plus the slope times the speed, or the variable you plug in, the x. Okay, so it'd be a plus b x. Okay, and if we did take the square root of that 99.8, we'd get an R of 0.99. So a very, very, very strong positive correlation, which makes sense. Your speed is definitely going to affect how many steps you're taking. Okay, realize that the slope of 0.080284 and the y-intercept of 1.7668 are statistics, which means they're estimates. They are not population parameters. If we collected another set of similar data from maybe 7 different runners, okay, and calculated our least squared regression line, the numbers would be different. They probably would be similar, but they're different because they're estimates. Okay, we don't know the true parameters for every single female runner out there. There is, in theory at least, a least square regression line for all possible data points that one could collect. Now we can't go out there and collect all possible runners. Okay, somebody that doesn't run could now become a runner. We just couldn't, but we could theoretically find that. Okay, if one could calculate the equation of that line, the slope and the intercepts would be parameters. What we can do, however, instead is to use our statistics to calculate a confidence interval. Ding, 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 same stuff we've been doing for these parameters. Note, the standard error for the statistics are provided in the computer printout. So just like I said, we'll use it up here. Okay, our standard error is 0.006 with our slope of 0.080284. And remember, our slope is telling us how much the speed is changing the steps that they take. Okay, so there are 7 data points. Therefore, going back to what I already said, the degrees of freedom is 5. If we want a 95% confidence interval for the true slope of the least square regression line, we need a critical value t. Okay, and again, we're going to use t because we're guessing on 2 separate things, the slope and the y-intercept. So it's not going to be quite accurate. So we need to find a t-score. And this t-score would come from our normal t-score, inverse t. And if we want a 95% confidence interval, we put in 0.975, and we'd get our t-score. Then, just like all the other times, a confidence interval is our point value, or in this case, our slope, okay, where b equals the slope, plus or minus the t times the standard error. And there is our confidence interval. Okay, so we are 95% confident that the slope of the true regression line for all runners out there is somewhere between 0.076 and 0.084. Okay? What if one is asked to interpret what this interval means? Okay, and it's what I just said, but I'm going to say it again. It could be said that we are 95% confident that each additional unit in feet per second increase in speed results in the number of steps increasing between 0.0762 and 0.0844. Okay, it's understanding what slope is. Okay, and so just a note on writing and interpreting slope of a least square regression line. Okay, right now we have a slope of 0.080284. And that's weird to say. We say that they increase 0.080284, but we'd really like to say for every 1 step they increase, or sorry, for every 1 meter they increase this many steps. So it turns out that the slope, m, is the same as 1 divided by 1 over m. If you simplified that, you'd just get m. And we're going to use this because we want 1, and let me double check that it's meters. What are we doing again? Oh, we're doing feet per second, excuse me. We want a 1 foot per second. So we're trying to make this numerator 1. Okay, so we could write the slope, if this was the slope, that's the same thing as 1 divided by 1 over the slope, and we get this. And so we actually could say that this, for each additional step per second taken by a female runner, because now we've made the numerator 1 step per second, her speed would increase by approximately 12.46 feet per second. Okay, so I kind of messed this up here, but does that make sense? What we're doing is we're making it something easier to say, and you don't have to do that, but if you want to, you could, to make it easier to interpret. The true regression line, okay, the actual parameter true regression line, which we can never find, is the mu of y, or the average y, is equal to some alpha plus some beta times x, or this is the parameter y-intercept, whoops, we have as a when it's a statistic, and b when it's a statistic, or the parameter y-intercept and the parameter slope or rate of change. Okay. Now we have to do some requirements before we could do a hypothesis test, and then we'll talk about why you'd want to do a hypothesis test. But let's look at the requirements first. The relationship between x and y is linear. We check by looking at a scatter plot of the data and a residual plot. Scatter plot should show a linear trend, residuals plotted against x or y hat, and they should look random. Okay, we also check for outliers and influential points. And we're going to do this in an example, but we just want to make sure that if you graph it, it looks fairly linear. Okay, it's not truly, it really wouldn't be best fit by something that goes like that maybe. Okay, the other thing we want to look at before we can do anything is the standard deviation of the response about the true line is the same everywhere, which means that each of these little points, excuse me, whoops, are about the same distance away from the line. There's not one really influential and maybe one over here really far away. Okay, they're about the same scatter away from the regression line. So let's read that. The scatter of the data points about the line. The variability should be roughly the same over the entire range of the data. Again, we can check on the residual plot. It is common to find that the y gets larger, so does the scatter of the points about the fitted line as theta is changing. We'll talk about that. Or basically, maybe it's kind of spreads out a little bit. Okay, but that's not as worrisome as maybe some high points. Okay, the next thing we want to look at is the response varies normally about the true regression line, and we'll talk about that in a minute. And that the data is a simple random sample or assumed representative of the population. So if we go back to the one we were looking at before, that the runners we're looking at are representative of all female runners. We don't have the top female runners or a bunch of them have been injured. It's a nice mix of all runners. When we are looking at a line of best fit, we have two statistics. We have y hat equals the y-intercept plus the slope. So we could do a hypothesis test for the y-intercept, or we could do a hypothesis test for the slope. And we tend to do it for the slope because it tells us more. And here's why it's important. Okay, the test of hypothesis that the true value of the slope is equal to 0. Okay, we test that it's equal to 0. Because a regression line with no slope, a regression line with a slope of 0 that's horizontal means that the y does not change at all when the x changes. So there is no useful linear relationship between x and y. So if you had a graph, okay, and all the points were like this, as x changes, y is not changing. That's like saying that there is no linear relationship, okay? Versus if there is some type of slope, then we can see that as the x goes up, the y goes up. There's a useful linear relationship, and we can use that to predict maybe a point over here, okay? So what we're going to do is we're going to test for 0 slope, and we're going to use that, we're going to use the test for 0 slope to test the hypothesis of no significant linear relationship between two quantitative variables. In other words, our null hypothesis is that the slope is equal to 0. There is no relationship. So then our alternate could be that it's greater than 0. There's a positive relationship, something like this. Or that it's less than 0, so there's a negative relationship or something like that. Or that it's just different from 0. Okay? And just like normal, we need some stuff. We need a test statistic. The test statistic t is given by the slope divided by the standard error of the slope. And then conversely or inversely, the standard error of the slope is given by the slope divided by t. Okay? And a small p-value means there's a strong relationship between the variables. Again, if we're going to do a test, and if we get a p-value less than, say, 0.05, we could say that the slope probably isn't 0, and that there is a relationship between the variables. Also, just like normal, for a confidence interval, we have the point estimate, or the estimate of the slope, plus or minus the t-value we could find, times the standard error. So we have point estimate plus or minus the margin of error. Okay. And we need to use the degrees of freedom of n minus 2 to find our t-value. You can read this later. So let's do an actual example on the next video.